Hello, welcome to this video. In this video we are going to define subspaces of a topological space. So let X be a topological space. Then we know that there is a topology associated with the non-empty set X, and that topology contains open sets which satisfy the axioms of the topological space. So X and to together can determine a topological space. We also consider a subset A of the set X. So let A be a subset of the set X. Now the question is, how can we define a topology on A? We can define a topology on this subset of X based on the topology already that exists in the space X. That topology, the newly that we are going to define the topology that we are going to define on the subset A will be called relative topology. Relative topology or the subspace topology. Subspace topology because it is called subspace topology because it's a topology defined on the subset of the set X. So but how can we define the relative topology or the subspace topology? See, we denote that subspace topology for convenience. We denote it by top prime. We know that open sets are there contained in the topology tau, and using this open set we can define the new topology, the subspace topology. So for that we have to consider the intersection of the intersection of all open sets, all open subsets of X which are present in tau with the subset A. So see, this is the definition for the new topology, the relative topology, tau prime. Tau prime then contains the subsets or the sets of the form O intersection A, where but what is O here? O is a member of tau. So here we have to consider each and every member, each member of tau need be taken here, and then its intersection with the subset A is determined. After that, after obtaining the intersection, that we know that that's a subset of will be a subset of A. Clearly, it's a subset of each element will be is a subset of A, and that. And that's a subset of that set is used is included in the new collection that is denoted by tau prime. So tau prime equal to set O intersection A, where O belongs to tau. The members of tau prime are called the relatively open sets. You know, they are also open sets, but these members, the members are of the form O intersection A, and these members are they act as open sets in the subset A. They are called the relatively open sets. And the common name of the members of tau prime is the relatively open sets. We sometimes we call it open sets. We simply call it open sets for convenience. And then we can consider the pair A and tau prime, A together with the tau prime, and that will be good, and that will make the subspace topology. So this is the definition of the subspace topology of the subset of subset A of the set X. For an example, let's consider, say we have an example here let's consider the non-empty set X that contains 5 elements A, B, C, D and E. And this is the topology we take on the set X, and the topology tau that that it must contain the entire set X and then null set phi, and then here we consider the element A set, the subset of this set ABC is set ABC, and then after that we consider AB to include in the topology, so set AB, and finally set C. So how many elements are there in the topology? These are open sets. See, 1, 2, 3, 4 and 5. See, there are 5 subsets of the set X which are included in the topology tau. And we consider a subset of the subset A of the set X. Let A be a subset of the set X. That subset is B, C and D. Here see, we choose the elements B, C and D to include in the subset. Then the question is how can we determine a topology for this subset A? See, that is explained here. See, top prime, we can call that topology top prime, and top prime is obtained by taking the intersection of the members of a tau with the subset A. So see, first element is X, and we take the intersection of X with the set A. Then what we are going to get. We are going to get B, C, D, the set B, C, D. Why? Because X is the entire set X. X is the entire set, and it's a subset. A is a subset of X. So you are going to get A as the intersection. And when after that we need to take the intersection of A with the second element, then we take the intersection of A with the third element, and next we take the intersection of A with the fourth element, and we take the intersection of A with the last element. Thus we get, see, top prime. We get that these are the members of top prime. The first member is BCD, second member BC, set BC. Why? Because it's the intersection of see, there is it's the BC is the intersection of BCD with ABC. So it's a set ABC, the intersection of set BCD with the set ABC. Okay, and then one element is missing. Unfortunately, it's missing. That is phi is missing here. That's a mistake. So you have to include the empty set also. But when it is written here, 1, 2, 3 and 4. There are only four subsets here in top prime, but in the next line, when it is written, then phi is also written. Now there are 5 elements. So this is correct. There's a mistake. That mistake is that phi is missing here. So you may correct it. Thus, you can see that by taking the intersection of A with each element of the topology tau, that is the topology of the given space X, we can obtain the relative topology of the subset A. Now we are now going to face a question, a problem. We are going to show that top prime is actually a topology for the subset. It's a topology for the subset A. We want to show that actually top prime can make a subspace. Initially, A is a subset. A is simply a subset of the topological space X. But in this way, if you define top prime, if top prime is defined this way, you can show that top prime acts as the topology. It makes a topology for the subset A, and thus it can then convert A into a subspace. So it can then make a topological space. And then only after verifying that, only after verifying this fact, we can say that A is a topological space. So until then, we will call that A is a subset. But we can verify how topology, how top prime acts as a topology for A. First of all, we want to verify that top prime contains the null set and the entire set here. Here for A, when we consider A is the capital A is the entire, the full set. So phi and A must be there. That is very easy to show. It's because in the topology tau, you know that phi is already present. So when you take intersection of phi with A, then you get phi as the answer. So this element phi, the null set, will be present in top prime by taking the intersection of phi, which is present in tau. In tau, see, phi is present in tau already. So by taking its intersection with A, we get phi, and that phi will be then present in tau prime. Next, you can show that A is also present here. The full set is the entire set here is A, is the subset of X. That you can show that it's also present in tau prime. Why? Because X is the entire space. X is present in tau prime, in tau here in this topology. X is present. So by taking X's intersection with A, we get A as the answer. So A is present in tau prime. And thus both phi and X are present in tau prime. That means they are open sets. In the case of A, with respect to the subset A, they can access, or they make open sets. Okay, and only after verifying that tau prime is a topology. See, we are only in the first step. Only after completing that verification that whether tau prime is a topology, we can say that phi and A acts as open sets. But see, we can now accept that they are phi and A as members of tau prime. Next, we are coming to the verification whether whether any family, means arbitrary family, whether any member of any collection of members of tau prime is also a member, any collection, and we take its union. See, union of any collection of members of tau prime is also a member. That point we want to verify. What is the point that we are going to verify? Here we are going to verify that whether the union of any collection, any collection of members of tau prime is also a member of the same collection. See, for that, when we take any collection, then you can take them as see O alpha, where where alpha is used to index the or to label the open sets. So O alpha, you know that when we take members of tau prime, and all the members have the form O intersection A, why? It's because we know that in the definition of tau prime, we have chosen that. See, how do we define tau prime? We have taken that it has the collection of O intersection A, where O belongs to tau. So it's very clear that when we choose a member from tau prime, then it has the form O intersection A, where O is some open set in the topology tau. And also here we know that we are taking any collection, that means that may be finite or infinite. See, an arbitrary collection of members of top prime is taken, and after taking that, we are going to find its union. So here we are going to write it like this. See, O alpha. So we want to label them in order to give clarity to the selected member of the topology top prime. So see, or the collection of the family. See, for the time being, let's call it the collection top prime. From the collection top prime, we are choosing members, and we are giving them labels. So alpha 1 intersection A, the first member will be, first chosen element is alpha 1 intersection A, and the second element is if an element is chosen, then alpha 2 intersection A, third element will be alpha 3 intersection A, and then like that it will go like that. So alpha, then in general we are choosing alpha the first element will be O1 intersection A. That's a mistake that that what I explained. There's a mistake. See, it must be corrected, like O1 intersection, the first element chosen is O1 intersection A. Then the next element is O2 intersection A, third element is O3 intersection A. Likewise, we are choosing the alpha after alpha selections. At the alpha stage, we are choosing O alpha intersection A, and that selection may not be finite. It may be infinite. So after choosing that members of top prime in this way, we are finding its union. So union of alpha, a union is taken over alpha, because alpha is used to represent what we can say, an arbitrary element of an arbitrarily chosen element of top prime. So this is the representation. So union is taken over alpha of O alpha intersection A. Then that can be written as written equal to union of O alpha. See, all the first part can be taken and it can be written as the union. It can be we can write it, so we can find its union taken over alpha of O alpha, then intersection. After that, you can find its intersection with A. So this is the simplification, and then you know that this is happening in tau. Then by treating O alpha, these are open sets in the topology tau for X. And so since tau is a topology, already we know that tau is a topology. We know that using the second axiom of the topology, any collection, union of any collection of open sets. This is the union of an arbitrary collection of open sets chosen from tau. So union over alpha of O alpha. This part will be an open set, and it belongs to tau. So this is that means this set, the union of this collection of union of open sets will be a member of tau. So it's a member of tau, and that means it's an open set. Then an open set intersection A. That means it takes the form. So this is in the form an open set intersection A. So it can belong to top prime. That means this union belongs to top prime. Next, we have to show that any finite family intersection of any finite family of members of top prime is again it's again a member of top prime. So as in the previous step, we are choosing open members of top prime So it has each and every member has the form OI. So on an open set intersection A, since we are choosing only finite number of members, and that can be written as OI in OI intersection A, where I varies from 1 to n, because we are choosing only limited number of open sets. Limited number of members of tau. See, we are choosing only a limited number of members of tau prime, and then we find its intersection. See, intersection where I varies. We have to consider all the members from 1 up to n. All of them must be included in this intersection. So intersection I varies from 1 to n of OI. OI it's a typical element. So OI intersection A, it equal to this can be then simplified to write it as it's equal to intersection. We know that using that dot result of this type, then intersection I varies from 1 to I varies from 1 to n of OI. Then it's then it's intersection inside, and then again intersection of A. It's because A, we have intersection with the A of each open set. So see, now we know that since tau is a topology, using the third axiom of the topology, we know that finite intersection of finite collection of open sets of tau is again an open set, or it's again a member of tau. That means it's an open set. So an open set which is a member of tau, intersection A is the answer. That means this intersection, the left hand side intersection of which is present on the left hand side of this expression is again a member of tau prime. That is tau prime. So tau prime, the members of tau prime, tau prime is a collection of subsets of A, and all these members satisfy all the three axioms of the topology. So tau prime can become a topology. We can now call the members of tau prime as open sets, but open sets where open sets in the subset A. These are the members of tau prime are all open sets in the subset A. So tau prime can make a topology of A. Thus we have proved that tau prime, which we defined in the beginning, can make a topology of the subset A. Okay, thank you.